Hey guys, welcome to Design Automation Conference 2019, LX booth number 623. We are here. I'm going to take you through the CocoTB verification methodology, how it is useful and how it is different from system Verilog, Verilog, UVM, such methodologies, and how distinctive it is and how it can be useful. So let's go through the presentation slides and talk more. Thank you. Hey guys, so to start off with, there is basically different types of verification. To talk about, there's function simulation, timing simulation, in-device testing. What Riviera-PRO offers, in that way, we are going to talk about the functional simulation, which has simulation, co-simulation, and hardware acceleration, or we call it emulation. To move on, the basic goal to do any chip level verification or FPGA level verification, what matters the most is 100% code coverage and 100% functional coverage. When you achieve that, you can say that you fully verified your chip level design or the DUT, design under test, and you can move on. There are several methodologies out in the market, such as system Verilog, UVM, which provides assertions to check as well. And then, of course, there is code coverage and functional coverage. To move on, the code coverage has different types, such as statement coverage, branch coverage, path coverage, toggle coverage, expression coverage, or condition coverage. These all sort of coverages have been supported on the platform Riviera-PRO, which is available to the users on evaluation. You can reach out to the sales team. And to move on, for the functional coverage, that the basic difference, to elaborate, code coverage is only telling you how much your DUT or the design code has been tested, while the functional coverage really tells you how much of the code you write was really corrected and covered. To give more specific example on the difference between the code coverage and functional coverage, let's say if you have 5-bit register value, and that means there are 32 possible values for a variable, and if you're randomizing and asking for the simulation, so if you are not going to use functional coverage, then possibly there might be 32 different values, 32 times the values will be generated, but they might be repeating, but you can't say that each and every value has been covered. So what the functional coverage really does, distinctively apart from code coverage, is that it finds out that each and every possible value has been covered, and that way you can really make sure that the verification was thorough and true. That can be directed and random testing. That's exactly what we talked about. Directed means passing the test vectors to the stimulus ourselves by giving the values to the design inputs, while random testing means declaring variables rand or randc. Rand is basically just declaring them random, and randc means making sure that the values are not repeated. There can be assertions that could be used, which is only supported on system Verilog and UVM. Assertions are asserted to find failing properties and covers to make sure properties were verified thoroughly. And there can be a scoreboard, and basically a layered testbed structure can be used as part of system Verilog and UVM, through which you can make sure that the verification was completed. It uses basically the object-oriented programming concepts, and there are drivers, generator, driver and monitor and scoreboard, regression testing, everything is there. Moving on, when we achieve 100% code and functional coverage, we can say the verification has been thorough. So this slide basically tells about the languages and the methodologies that are out in the market. VHDL, system Verilog for design, system Verilog verification, UVM, Python, CocoTB for high level of abstraction, co-simulation, co-emulation. These are all the methods through which you can verify design. Moving on, with the latest technologies out there in the market, designs are becoming very complicated, and there are so many transistors used, millions and billions of transistors used as part of one design. So it's really important that you use and you choose the right methodology for the verification purpose. So here we are going to talk about, everybody's aware of system Verilog and UVM, but nobody knows what actually verification methodology using Python as well. So CocoTB is basically a high-level abstraction verification methodology, recently out in the market, which is open source, so anybody can use it, and it's totally coroutine based. So especially for users who are embedded design engineers or coming from a software background, they can also try it out and make themselves comfortable with the verification of HDLs. It's basically a great replacement of system Verilog UVM. Not at par, but it's still developing. So system-A, UVM are OOP based, and UVM libraries are there for scoreboard sequences, sequence items, and everything. They are transaction level, constraint random, and coverage driven. And then there are also automation scripts, compile chain files only, resimulated design, self-checking test bench, self-scoreboard, and auto-generated coverage logs and trace to test the plan as well. Now this is what CocoaDB is. It encourages design reuse and randomized testing similar to UVM and System Verilog. HDL design support with Verilog, VHDL, and System Verilog, meaning that a user can have a design based on Verilog, System Verilog, or VHDL as well, and they can do the verification using Python CocoaDB. So it's not that somebody has to do the design as part of the Python as well. You can still do your design using the HDLs, and you can verify them using CocoaDB. There is built-in support for Jenkins integrated system, meaning that if regression testing is possible, so by the time at the end of the day, if somebody wants to verify the design, they can run the test. They can keep on running them, and in the morning probably they can collect the results, which is only possible using CocoaDB, as it's supported with the Jenkins. It has the interpreted environment support using Python, and it's faster for simulation. Thus, CocoaDB is really great and affirmative possibility in terms of verification technology. As you can see in the screen, this is how the GUI, the batch mode window looks like. You write the right commands for the simulation process of using CocoaDB, and then you can watch the results being executed as part of the batch mode. And this is in association with Riviera-PRO. So once the simulation finishes, you can use the coverage database or the simulation database and open it as part of the GUI and watch the results as part of the waveform viewer. This is how exactly it looks like, and it's exactly how easy it is to use. Similar results approach like System Verilog, Verilog, VHDL, UVM. So I really believe that this is going to be the future, especially for considering the fact that the embedded world and the ASIC and the FPGA worlds are collaborating more and more together. It's important that CocoaDB is given enough importance. For more information about Aldec software, please visit us on www.aldec.com. Thank you.